Thank you very much, Giovanni. Thank you very much for your invitation to the Italian chapter and for this this great initiative that you had. This is extremely beneficial for everybody, especially in this time of crisis. So, I mean, I believe that everybody here is aware of the IEEE Magnetic Society. So I can only encourage you to to get more involved, especially to pay attention to the next Intermag meeting in 2023 in Sendai. And hopefully we'll be able to meet in flesh over there. So I just want to say one word before moving on, that the presentation I'm giving today is kind of a mirror presentation of another IEEE distinguished lecturer, Jingshen Chen, who is a collaborator and is going to talk also about this symmetry breaking in certain materials for spin-orbit torque. So as you can see here, the original plan for this presentation was to address a broad audience of people who may not be fully aware of the state of the art of spintronics. As I've been following the many presentations of the petaspin, I believe that well, the audience is actually fairly aware of what spintronics is. So I will spare you with the introduction. And I will directly jump to the second part of this presentation, which is about spin-orbit coupling. The objective being to move on to spin-orbit torque and Joystick-Murray interaction, and particularly have a look at how they can be modified in specific low symmetry systems. So well, let's move on to number 2. So as you are all aware of, actually magnetization has a lot to do with angular momentum. And this is actually something that was first pointed out by the Einstein-de Haas effect, you know, where you actually take a material, a paramagnet, you apply a magnetic field to orient all the isolated spins, and through this orientation, the setup of the magnetization results in a mechanical torque. The reciprocal of this effect is the Barnett effect, where instead of applying magnetic field, you actually rotate or induce a rotation of your paramagnet to magnetize it. And these two effects are really two sides of the same coin, and pointing out that magnetization has a lot to do with angular momentum. And what we're going to talk about today is actually based on angular momentum conservation. I mean, that's the whole idea. So of course you can have a look at those papers here that actually give a deeper discussion of those different effects. So when we started to work on this field years ago, the idea was to find a way to generate torques by transferring angular momentum. And the idea is actually, again, you know, represented here by Einstein, where, you know, when you're on your bike, you want to turn left. Well, what you have to do is to create another angular momentum that actually compensates the one you're going to create. And you basically need to bend on your bike if you want to turn left. So you have to bend on the left. And spin-orbit coupling is essentially doing that in matter. So that's what I would like to talk about today. So if you take, I mean, I'm sure you're all aware, if you take a moving particle in let's say with momentum P in an external electric field, then in the frame of motion of this particle will experience a magnetic field. If on top of that, this particle has a spin, then you end up with a coupling between the magnetic field in the frame of motion and the spin of this particle, which is essentially the spin-orbit coupling. So here is the spin. You have the potential gradient, which is related to the electric field, and the electron momentum. Now, what is interesting is that in condensed matter, well, if you just take an atom, let's take a few one step at a time. You take an atom, then the potential is radial, which actually produces a spin-orbit coupling of the Russell-Sanders form, which is this traditional form where the spin is aligned on the orbital angular momentum here. Now, in condensed matter, in fact, most of the potential gradient, even at interfaces, in fact, is concentrated close to the atom nucleus. So what happens is that if you want to understand how spin-orbit coupling impacts the mass structure of your system, you have to project this atomic spin-orbit coupling on the block states. And when you do that, what you get is a Zeeman term where the effective field is momentum dependent. So if your crystal structure has inversion symmetry, then this momentum will be even in, the symmetric field will be even in momentum. And the only thing you can get is an anomalous velocity that is spin dependent, which is essentially the Magnus force you have, when you have a spinning ball that is in a flow of flow of air, for example. And this anomalous velocity here is connected to the Berry curvature, which is directly related to this magnetic field, effective magnetic field. And this spin-dependent anomalous velocity is the origin of the spin Hall effect, where spin up and spin down are separated in a transverse direction to the injected current. Now, if you actually break inversion symmetry, and that's of course very interesting to us at the moment, then this magnetic field becomes, well, you break the evenness of the magnetic field as a function of the moment, and you can actually create an effective Zeeman term that is odd in momentum. So here I just give you a very specific form of this Hamiltonian, which is called the Rashba Hamiltonian, where the spin is directly proportional to the magnetic moment, and Z here is a normal to an interface. So that kind of Hamiltonian is very specific to inversion symmetry breaking at interfaces, widely used in semiconductors. And we actually realized let's say about a decade ago or 15 years ago, that this actually can represent a lot of interesting physics for traditional metal spintronics. Now, what this Hamiltonian does is that when you have a flow of electron in matter, then the spin of this electron, as long as you have inversion symmetry breaking, the spin of this electron will align along one particular direction. So here I just pick one random direction that is along the transport direction, but of course it actually depends on the symmetry of the system. If you are at an interface, this equation tells you that the spin must be in the plane of the interface but perpendicular to the motion of the electron. So what I wanted to do when I started to work on that, a few years ago, I wanted to give a very simple model of this Rashba effect, this spin momentum locking effect in one dimension, to understand the role of the orbital degree of freedom in the onset of the Rashba spin-orbit coupling. So let's take a chain of atoms, and in this chain I'm just going to put a pz orbital and a px orbital, because if I mix px and pz, I know I'm going to have an angular momentum along the y direction, an orbital angular momentum. Now, you see that if I just take this chain, then the px and py orbitals are orthogonal to each other. So if I want to start mixing px and py, I need to break the inversion symmetry and, for instance, just add another chain on top, a dissimilar chain that's actually there. And you see that through the connection of the bottom orbitals to the top orbitals, I will end up mixing px and px and pz, sorry, thereby creating an orbital angular momentum along the y direction. So, the model, the actual Hamiltonian looks like that. You can find more details in this paper. But what is important is that if now I compute so it's a very, it's a 3x3 Hamiltonian. There is actually no spin information at this stage, okay? So it's only orbital information. You can get the eigenstate of the system and compute, for instance, the expectation value of your orbital angular momentum. When you do that, you do get that this orbital angular momentum is oriented along the y direction, which is what we were expecting. But because of the specific symmetry of the p orbitals, you see that this orbital angular momentum is odd in momentum. So this is not exactly the simple Rashba case, because of course we have block states in the game. We are not necessarily close to the gamma points, but you actually have all the essential ingredients. Now, if you turn on the spin-orbit coupling, then the spin will be locked on this orbital angular momentum, and you end up with Rashba spin-orbit coupling. In fact, you can, I just did this model for one-dimensional chain. You can You can try that. I mean, if you have some DFT experts here, they know very well how to do that in considering all the orbitals. Here I just show you the band structure projected on the orbital degrees and spin degrees of freedom of a bilayer that is composed of, well, that's what I call my fake tungsten, my fake iron. I just take the 10d orbitals. I use the Slater cluster parameters of the bulk material. So of course, there's a lot of, I mean, this is not supposed to represent a realist, I mean, a real iron tungsten bilayer, but at least it gives me something that is complex enough to represent a transition metal and to avoid obvious discrepancies of very, very simple models. What I see in those band structure is that, so this is the orbital information along the different path in the Brillouin zone. And what you see that the orbital degree of freedom, the Lx and the Ly degrees of freedom actually change sign along the, let's say this is the Ky path and this is the Kx path. So this is exactly like the Rashba effect we expect, except that this is on the orbital level. So this, of course, survives even if I have no spin-orbit coupling. Now, when I turn on the spin-orbit coupling, then I have the same information. This orbital information is mapped on the spin information, and I end up with the Rashba effect. I mean, the so-called Rashba effect, where the spin degree of freedom changes sign. Let's say here you have the Sx degree of freedom along the Ky path, and you see that you actually go from positive to negative values and vice versa. Okay, so when I'm going to take this bilayer, I'm going to inject a current through it, and then I can get all sort of interesting spin-orbit talk science. So now I just want to show you some of the results you can get in this kind of bilayer. So the kind of system we look at is a transition metal bilayer where you have some heavy metal on one side and some ferromagnet on the other side. And we know that the two important mechanisms we're going to get there is on one side the spin-orbit torque and the other side the Joystick-Schema interaction. So the Joystick-Schema interaction is rather an equilibrium effect, just magnetic anti-symmetric magnetic exchange, while the spin-orbit torque is a transport effect. So if I look at this interface, I actually should have those three main effects. They are not the only one, of course. I mean, there's still a lot of research on the actual physics of this effect. So if you take this bilayer here, you have your ferromagnet on top, your heavy metal on bottom. You're going to have this pinhole effect I was mentioning before in the bulk of your heavy metal, because in the bulk there is inversion symmetry. So you will have a separation of up and down spin, which will create a spin current that will be absorbed by the ferromagnet. And this absorption of the spin current will create what we call a damping-like torque. So it's a torque that is even in magnetization. Now, if you just look at what happens at the interface, then you're going to have this Rashba effect. Okay, this is actually fairly robust, as I just showed using this multi-orbital model. And finally, so this importantly, this Rashba effect enables the creation out of equilibrium of a spin density. And the torque due to this spin density would just give you what we call a field-like torque. So it's a torque that now is odd in magnetization, exactly like a field. Now, the third effect is the Joystick-Schema interaction, which is this anti-symmetric, the anti-symmetric magnetic interaction that if you write it in the continuous limit, this is actually interaction that is proportional to the gradient of the magnetization. So you can do that in three-dimensional materials and in two-dimensional materials. Here I'm just focusing on the two-dimensional systems. And in this case, we have this particular form that actually, has some reminiscence of the Rashba symmetry. Okay, you have the Z cross here and the Z cross here, just because the Joystick-Schema and sorry, there was a mistake. So Rashba effect and Joystick-Schema is actually coming from the same same spin-orbit physics. So of course we expect them to have the same symmetry. So if I apply, if I use my bilayer, so here I have a few information on how to build this layer. So we have all the 10 d orbitals. We have the Russell Sanders atomic spin-orbit coupling, some SD exchange, effective SD exchange. And once we have that, we can calculate spin-orbit torque and Joystick-Schema interaction. So here is the current-driven spin density across the layers. So you have the ferromagnet here, and you have the heavy metal. So if I put spin-orbit coupling everywhere, let's only focus on this case. This is the black curve. You're going to have here the SX component. So the magnetization is along Z, and you send the current along X. So this one is a spin density that gives rise to the damping torque. This one is a spin density that gives rise to the field-like torque. So we would expect that the spin Hall effect is rather here, and the Rashba effect is rather here, okay, on the bottom. So you can, I mean, look at the influence of the disorder, and in fact, the field-like torque, this guy, is mostly extrinsic, while the damping lag torque, this guy is mostly intrinsic. So this is the damping lag torque, the SX component, is related to Berry curvature in the spin momentum space. So that's so essentially this is, we have a much more complex setup, and the conclusion is that, well, what we have been saying for years about those two effects is mostly working fine. Now, what is interesting is what happens when you start changing the thickness of the system. And this is something that is pretty hard to do with density functional theory, because you have many orbitals to take into account. So, I mean, it's possible, it's just extremely computationally demanding. And so I will actually focus on the thickness dependence of the normal metal. So you typically have platinum cobalt, and you change the thickness of your platinum. Okay, we'll not talk too much about changing the thickness of your cobalt layer of your ferromagnets. I mean, you have some dephasing, but I would say this is kind of expected. What is interesting that if I look at the speed at the field-like torque, when I change the thickness of my heavy metal, nothing changes, except of course if I go to very thin layers, then I'm going to have quantum oscillations. But if I go to reasonably thick layer, then the field-like torque is completely flat, which means that adding more matter with a lot of spin-orbit coupling doesn't help getting me any new torque. And that makes sense because this is purely an interfacial effect. Now, the damping torque has a different behavior. If you go to, I would say, rather thick ferromagnet, I mean, heavy metal, then of course you saturate, which makes sense because you have all the matter contributing to your torque. But if you go for very small thicknesses, then you actually even have a chain of sign, which I think is quite specific to this particular model. But most importantly, for very thin layer, you still have a damping torque. It's not very large, but it's actually still here. And this is really coming from the interfacial contribution of Rashba plus magnetism. Okay, so that's an important, I think, an important element that we can learn from this kind of calculation. We can also move on to calculate the Joystick schema interaction. So for that, we need a Green's function formalism if we want to use this this model. I mean, there are other methods, but I'm going to use this one. So we use Keldysh formalism and get some nice Green's function formula. If we apply this formula to the Rashba, magnetic Rashba system, then we retrieve the symmetry I was mentioning before, which is really the Joystick schema area you would expect for an interface. Now, the question is whether in our model, the interface, this effective Rashba picture works, and indeed it does. So, I mean, of course, here I cannot go through all the details, but you have to trust me here. We basically check that the symmetry of our Joystick schema area interaction does respect the Rashba model. We can again, vary the thickness. I mean, there are quite long calculations, but this is possible. And what is interesting is that if you change the thickness of the heavy metal that's here, you actually realize that there is a smooth oscillation of the Joystick schema area interaction, which really means that there might be some long-range contribution. Maybe not too long, but still, I would say long enough. It's not purely interfacial, at least. So that's an interesting point that we would like to address in more details in the future. So these elements just give you some important information of what to expect for spin-orbit torque on Joystick schema interaction in transition metals. Now, what I would like to do is to move one step forward and break even more symmetries. Okay, at the moment I have only considered inversion symmetry breaking. Now I'd like to see what happens when I break even more mirror symmetries, let's say. So as we know, from Neumann's principle, that was actually enunciated by Voigt, for the symmetry of the physical phenomenon or phenomena we're interested in is at least as high as the crystallographic symmetry. So we can actually use the crystallographic symmetry to extract the form, the general form of the tensor response. So we talk about torque, damping, Joystick schema area. They all have a particular symmetry, and we just by applying high symmetry principle, we should be able to extract this information. So this is actually something that was initiated in the field of spin-orbitronics by Wimmer and coworkers and Železný and coworkers. So I really encourage you guys to have a look at those papers. They're really very deep, and they give you all bunch of tables and about the response tensors for the torque and for the conductivity and so on. So we probably need also to do that with the Joystick interaction, though. So for instance, you can train yourself and look at very simple system. Let's say if you only have a two-fold rotation or just a mirror symmetry, then you can extract the form of the field-like torque, for instance. Here I just give you an extract of the table that was computed by Jakub Železný he actually visited all the pound groups and extracted the field-like torque tensor form as well as a damping-like torque. So it's actually extremely efficient, very, very useful. And if you start taking some crazy materials into account, then you can actually you don't get the physics inside, but you get the general form. So two examples of low symmetry system have been produced in the past years. So the manganese nickel antimony by Chiara Ciccarelli, where they were basically able to identify that from the symmetry of the crystal of the material, you should have a Dresselhaus-like and a Rashba-like spin-orbit torque. So they were actually able to measure. So this is the measured spin-orbit torque, and we see that it's actually a combination of Dresselhaus and Rashba torque. There was also a very nice work by Dan Ralph's team in 2017 on tungsten ditellurium permalloy bilayer, where the tungsten ditellurium has a very strong crystalline anisotropy. And this anisotropy, so you have actually a mirror symmetry that is only on one particular direction. If you inject the current perpendicular to this mirror symmetry, you actually end up with a perpendicular damping torque. So this is okay. You have to be experts here to understand that this is a perpendicular damping torque. But I encourage you to have a look at those papers. So if you inject the current perpendicular to this particular symmetry, then you end up with a damping torque that is perpendicular, which is of course not expected in those bilayers. So this is really something that Rashba's theory cannot cover. You also have some very strong anisotropy. I will not comment too much on that because I really need to move on. And I'd like to mention a recent work that we had in collaboration with Jingjin Chen at NUS, where they were actually considering the L11 bilayer. So it's a bilayer of copper platinum, cobalt platinum and those materials are in the L11 configuration, which has this kind of symmetry. So if you look at the crystalline group, it's actually a trigonal 3 bar M. And what they were able to observe is that, they were actually doing the current driven switching, and depending on the direction of the current with respect to the high symmetries axis of this crystal structure, they were able to get either switching along one direction, no switching, switching along the opposite direction, no switching again, and so on. So they actually kind of have an oscillation of the switching efficiency from plus to minus. You can really change the polarity. And this is something that we wanted to understand. So you take the point group of this bilayer, which is essentially 3M, and you either look at the Železny's paper, or you just do it by yourself, and then you end up with this kind of torque. It's a damping torque. This is just regular damping torque. Nothing is surprising here. But what is interesting, this first term here, where this term is entirely due to the threefold symmetry plus mirror symmetry. I just want to mention that this was also predicted by Arne Bratta's team from iron 3, germanium, tellurium 2. There's a 2 here that is missing. And what is this torque doing? It's actually quite interesting. So let's imagine that you are in the perpendicular direction. I'm injecting a current, let's say I'm applying an electric field on one particular direction here. Then of course, this damping torque will bring the magnetization in plane. Okay, so I get in plane. Once I'm in plane, then this torque is triggered. And depending on where the magnetization is oriented, the torque will either bring it back to its original configuration, or, so no switching, of course, or along, let's say, if you apply the electric field along the 30 degree, in this case, the magnetization goes perpendicular to the electric field and you get no torque at all. It's just a matter of symmetry. You can look at this guy, you put the right angle of the magnetization, get no torque. But finally, if you actually go along 60 degrees, then the magnetization is in such a direction that the torque is actually positive and completely switches the magnetization. So then you end up, depending on the direction, you end up with, I mean, either one polarity or the other, or no switching at all. Now, it turned out that these the 3M symmetry is actually also has some very strong impact on the Joystick schema area, and this will be the last information I wanted to share with you. So we actually looked at the iron 3 germanium 2 crystal structure, because there was at some time there was a claim that, I mean, skyrmions was observed in those structure, which was very surprising to us, because you have a very strong mirror symmetry. So we wanted to understand where the torque is, I mean, the Joystick schema area is coming from in this structure. So you do have this six-fold improper rotation plus mirror symmetry. I mean, everything looks fine, but I was not expecting this nail-like Joystick schema area interaction. So it turned out that there is a deep connection between the symmetry of the damping torque and the symmetry of the Joystick schema area interaction. So you can take this torque, apply this symmetry connection that was actually first pointed out by Frank Freimuth, and then extract the tensor of the Joystick schema area interaction. So this is actually the same tensor as the damping torque. When you do that, you can get the Joystick schema area expression, which is here. And when you try to see if it can be helpful at all, well, you realize that this Joystick schema area interaction doesn't do anything at the long range. So we are still trying to find, you know, if there was anything interesting to do. So we performed spin spiral calculation using the generalized block theorem. So this is actually the spin spiral dispersion in various configuration. And we found that when the spin spiral is a nail in plane, so this is this kind of spin spiral in plane, you actually do have some Joystick schema area interaction on the short range. So concretely, what does it mean? It means that in this kind of crystal, you can stabilize in-plane spin spiral, because when along low symmetry directions, you see, if I take this direction here, you see that it's actually a low symmetry direction, because there is no mirror. I mean, the mirror symmetry is broken here. So those two paths are inequivalent. In this case, I can actually stabilize an in-plane spin spiral in principle. So I reach now the conclusion of my talk. So I would like to thank you all for listening. I apologize for being a little bit late. And I would like to thank all the people who have been contributing to this work, either students, postdocs, and collaborators.